I welcome all of you to the video lecture series on fluid mechanics. This lecture is on topic 2 on fluid statics. This is the last lecture corresponding to the topic 2 on fluid statics, corresponding to the last section on engineering application. We started this topic on fluid statics on with pressure, what is the direction of pressure when it acts on a surface and pressure at a point. And then we went on to deriving the governing differential equation for fluid statics, which is the first order ordinary differential equation for pressure, and which we integrated and obtained a solution for pressure distribution in a stationary fluid. The pressure distribution we have finally applied for certain engineering applications, such as manometer, which was presented in the previous lecture, and the second application, which corresponds to force on hydrostatic force on submerged surface, which is the title of the present lecture 10 on engineering application for fluid statics. So the present lecture is on hydrostatic force on a submerged surface. So whenever the stationary fluid interacts with a stationary structure, there is a certain hydrostatic force which acts. There are fluid dynamic forces which acts, but when we say hydrostatic, we mean a liquid is interacting with a stationary solid surface. So hydrostatic force corresponds to interaction of the stationary liquid with a solid surface. While defining the fluid mechanics, I had mentioned that a stationary fluid or a fluid in motion interacts with a stationary solid or a solid in motion. Here for the topic on fluid statics, we are considering the fluid as stationary as well as the solid as stationary. Now the interaction of the stationary fluid with a stationary solid surface, this results in a hydrostatic force. When we consider the interaction of a liquid with a solid surface, we call it as a hydrostatic. When a gas interacts with a solid surface, we call it as an aerostatic. So here we are considering the stationary fluid interacting with a solid, and that's why we are calling the force which is generated as a hydrostatic force. So the effect of the stationary fluid which is wetting a solid surface is the hydrostatic force on the solid surface. In my previous topic, I had mentioned that in fluid mechanics, you should pay particular attention to the effect of the interaction of a fluid with a solid. So in a fluid statics, note that the effect of a stationary liquid on a solid is it results in a hydrodynamic force. Now, in this lecture, we'll consider two types of solid surfaces. A fluid which is wetting a plane solid surface and also a solid surfaces which are curved. So we'll consider both plane and curved solid surfaces. Now the example of the hydrodynamic force due to interaction of a stationary fluid with a stationary solid surface are shown here. The first example corresponds to wall of a tank or dam. The second example corresponds to hull of a ship. And third is valve in a dam. Note that in all these example problems, like if you consider water in a tank or a dam, on one side of the wall you have water, on the other side you have air. Similarly, in case of hull of a ship and valve in a dam. So we are interested in the hydrostatic force which is acting on the surface of the tank, hull of a ship, and valve in a dam. These problems corresponding to dam, ship, and are commonly encountered by civil engineer. This figure shows a column of liquid which could be corresponding to a dam, and we have a vertical surface. This could be a this vertical wall can be wall of a dam or it could be wall of a tank. Now, in this figure, notice that on the right surface of this wall, everywhere you have atmospheric pressure. And here in this, on the top surface, you have an atmospheric pressure. And as you go down, as discussed in the previous topic, in the deeper layers, the pressure increases. And in the previous topic, it was shown that there is a linear increase in the pressure. So the linear increase in the pressure is shown here. Now, so this figure shows you the pressure distribution on the left and right surface of a vertical wall, which is shown here. Now, since both left and right side of this vertical wall is subjected to the atmospheric pressure, so if you subtract the atmospheric pressure, then you end up with a pressure distribution as shown here. So this corresponds to a gauge pressure. I mentioned the definition of the gauge pressure in the previous topic, where we measure the pressure with reference to atmospheric pressure. So if you consider the atmospheric pressure, then for this column of liquid, the pressure distribution corresponds to P atmospheric plus rho gh. And this is the absolute pressure. And for the column of liquid, this is the gauge pressure. In most of the problem for this topic, we will be subtracting this atmospheric pressure to calculate the net hydrostatic force which is acting on this on the solid surfaces. We will consider, as I had mentioned, hydrostatic forces on two types of surfaces, plane surface and curved surface. Let us start with the plane surface. Now, whenever you want to calculate a force which is acting on a surface, then you are interested in its magnitude and its point of application, as shown here. So the resultant hydrostatic force, you are interested in the magnitude, which is denoted here by Fr, and the point of application, which is denoted here by Yp. What is this Yp? I will show you through a figure. The point of application of the resultant force is also called a center of pressure. So let us suppose you have an inclined plate. This is your inclined plate, and on this is shown in YZ plane. The plate in XY plane is shown here. So perpendicular to this plane, this is the X direction and this is the Y direction. So two different views are shown. This is like a front view and this is like a top view of the inclined plate. So we are considering an inclined plane surface. This is the front view and this is the top view. Now this plate is inclined at an angle of theta from the horizontal direction, which corresponds to the free surface. Let us suppose this is a water column and this is the free surface, and this solid surface, this inclined plate, is supporting this water column. Now the pressure distribution, I had mentioned that the pressure on a solid surface, acts normal to the surface, and pressure at a point is a scalar quantity. So here the pressure is shown acting on a solid surface, and you can see that they are shown normal to the solid surface. And since this this point is below this point, so as you go down, the pressure is increasing in deeper layers. So this shows the pressure distribution on the surface of the plate. Now, to calculate whenever we have so this represents a parallel force system, and in a parallel force system, now we have to calculate a resultant force. or to calculate the resultant force, basically we will integrate this pressure distribution. So all of you know this, that we'll basically do an integral of local pressure distribution with an, so we'll start with an elemental area as shown here, and we'll apply integral of PD. So in this small area, there is a pressure which is acting. So this pressure is given as this elemental area is located at any arbitrary location y. Note that we are using this YZ coordinate system where y is inclined along the y coordinate is along the length of the plate. And for this elemental area, the pressure is equals to P naught. Now this P naught is the pressure at free surface. For most of the problem, this P naught is equals to the atmospheric pressure. But if the free surface is exposed to a gas which is at a different pressure than atmospheric, so we are taking a general case, but in most of the cases, this P naught is an atmospheric pressure. And this is the absolute pressure. So absolute pressure is equals to pressure at the free surface plus rho g h we take. So now this h height is equal to, for this problem, height is equals to y sin theta. So the height of this elemental area corresponds to y sin theta. So this is given by P naught plus rho g h, as I mentioned, is equals to y sin theta. Now when you integrate, integral of P naught dA will be P naught into A. And then when you integrate the second term, you will get rho g sin theta, which will come out of the integral sign, since it's independent of area, and you get integral of y dA. Now this integral of y dA is the first moment of area, and it is represented as the product of the y coordinate at the centroid multiplied by the area of the plate. So this C represents the centroid, and it is marked in the figure as shown here. And the location, this location is, this is the YC which is used here. Now this YC sin theta, as I had mentioned, this YC sin theta corresponds to, I have mentioned y sin theta as h. So YC sin theta will be equal to HC. So you get, so note that you are getting P naught plus rho g HC into A. Now this pressure, so the resultant force we have derived that the resultant force is equals to pressure at the centroid of the plate multiplied by the area of the plate. So the resultant, if you, for any problem, if you have to calculate the resultant hydrostatic force, basically you do not bother about the pressure distribution on the surface of the plate. You just consider one point, which is the centroid of that plate, and determine the height of the centroid of the plate from the free surface, and using that you can calculate the resultant force by considering the free surface pressure plus rho g, the height of the centroid. So you need to bother only about the pressure at one point rather than getting involved with this pressure distribution. So this is about the resultant hydrostatic force on an inclined plane surface. Now, the next we have to obtain the point of application. Now, this resultant force, to determine its points of application, we know that two parallel force systems are equivalent if they have the same magnitude and if they have same moment above any point. So what we will do is that we will take the moment of the resultant force and this distributed pressure system with respect to this point, which I will call as O. Let us suppose this This is the center of pressure, and this is located at a y coordinate yp, and this is the point of application of the resultant force. This arrow represents the resultant force Fr, and its point of application corresponds to the coordinate yp, which is shown here as center of pressure. This yp is determined by equating the moment of Fr to the moment of the distributed pressure force across about the x-axis. X-axis is perpendicular to this plane. So we will take this is the moment of yp. So we are taking the moment about this point. So this Fr into, if you take a moment from here, Fr into yp is equals to moment of the distributed force system. So that is equal to integral of yp dA. Now pressure, if you substitute at any height h, you have h is equals to y sine theta. So this will be y, this pressure you are substituting P0 plus rho g y sine theta. Now in this you will get P naught. Now this has two terms in the integrand, and you will obtain P naught integral of y dA plus rho g sine theta integral of y squared dA. Now earlier I had introduced first moment of inertia here. Now here you can notice a second moment of inertia, which is called second moment of area, which is also called as moment of inertia. So you encounter moment of inertia to calculate the point of application of the force. Now this moment of inertia is about this point O. Now we are interested in, whenever you have a plate, you can calculate, like for a rectangular plate of size width A and height B, the moment of inertia about the centroid, we know that it is a b cube by 12. So for most of the plane surfaces, we know the moment of inertia about its centroid. So what we do is that, although here we are getting the moment of inertia about the x-axis which is passing through this point O, by using a parallel axis theorem, where the distance, what we do is that, where we take the distance between O and the centroid, which is yc, and by using parallel axis theorem, we know that Ixx O is equals to Ix, moment of inertia about O is equals to moment of inertia about C plus the distance between O and C, which is yc, square into A. So when you substitute it here, you get, so this is equals to P naught yc A plus rho g sine theta Ixx about the centroid plus rho g sine theta y square A. So basically, by using parallel axis theorem, once you substitute it, you get this expression. Now in this expression, this yc A is common in this two terms. So if you take A and yc common, then you get P naught plus rho g sine theta into yc and A. Now what is this rho g yc sine theta? Yc sine theta, we know yc sine theta is hc, which is the height of the centroid, and rho g into height of the centroid plus P naught gives you the pressure which acts at the centroid, and the pressure which acts at the centroid, which is shown here, multiplied by area, is equals to Fr. So this total term is equals to Fr, and then it's multiplied by yc. So this is Fr into yc. So on the left hand side you have yp into Fr. On the right hand side, the first term becomes Fr into yc. When you divide the Fr on the right hand side, you finally obtain yp is equals to, this Fr cancels down from the right hand side, and you obtain yp is equals to yc plus rho g sine theta ixxc divided by this whole term p naught plus rho g yc sine theta into a. Now the rho g sine theta term is common in the numerator as well as denominator. So if we divide numerator and denominator by rho g sine theta, then in the denominator you get P0 divided by rho g sine theta plus yc into a as shown here. So with this, we have obtained the expression for the center of pressure. This is the point of application of the force. Note that it consists of two terms. First term, the y coordinate of the centroid, this yc which is shown here, and so yp is equals to yc plus a second term which is a positive term. This is the moment of inertia of for the plate about the centroid divided by P naught, which will be atmospheric pressure if the free surface pressure is atmospheric. Otherwise, in general, this is the pressure of the free surface divided by rho g sine theta plus yc, which is the y coordinate of the centroid, into the surface area. Note that the second term is positive, so yp is slightly below the y coordinate of the centroid. Center of pressure is slightly below the y coordinate corresponding to the centroid. Now let us take some special cases of the submerged rectangular plate. We'll consider three different cases: tilted or inclined plate, vertical plate, and a horizontal plate, as shown here. So this is a tilted plate, vertical plate, and a horizontal plate. Our interest for these three cases is to determine first the magnitude of the resultant hydrostatic force, and second the point of application, using the expressions which has been presented in the previous slide. So this plate is inclined at an angle of, tilted plate is inclined at an angle of theta, and the tip of the plate is located at a distance of s from the free surface, and the length of this plate is b. The dimension of this plate, this is a rectangular plate, the dimension of this plate perpendicular to this plane is a, the surface area is a into b. Here the pressure distribution on above this plate is shown. Note that for this problem, although this plate is completely submerged in a fluid, we are interested in the hydrostatic force which is acting on the upper surface of the plate. So on the deeper layer, the pressure increases, and as discussed earlier, the pressure on a surface acts normal to it, and it is increasing in the deeper layers. This is the pressure distribution which is varying linearly. The tip of the vertical plate is located at a distance of s from the free surface, and here again the length of the plate is b, and here the pressure distribution, which varies linearly, increases linearly with increasing depth, is shown here. Whereas when you consider pressure distribution on a horizontal surface, the weight of the liquid, which in a horizontal plate at different point, it is same. So the pressure which acts, hydrostatic pressure, is same. So the pressure distribution is shown as uniform in this case. Now in the schematics, I will show you for these three cases the point of application of the resultant force. So this is the resultant force Fr on the tilted plate, which is located at a coordinate yp. Yp is the distance from O to the location at which the pressure is acting. Okay. Now, for the tilted plate, the YP is as shown here. This is the coordinate of the point of the application from the free surface. In case of horizontal plate, this is the resultant hydrodynamic force, and in this case, for the tilted plate and vertical plate, note that the point of application of the resultant force is slightly below the y coordinate of the centroid. However, note that in case of horizontal plate, the point of location of this resultant force is midpoint, corresponding to A by 2, where A is the width of this horizontal plate. So using the expression which has been shown in the previous slide, now the expressions for the magnitude of resultant force is shown for these three different cases. For the tilted plate, as we know that the resultant magnitude of resultant hydrostatic force is equals to pressure at the centroid. Now, what is the location of the centroid? If you calculate the y coordinate, it will be s plus b by 2. The centroid is located on this plate at a distance of b by 2. So s plus b by 2, and the height of the fluid at the centroid will be s plus b by 2 sine theta, which is as shown here. So this gives you Hc. Rho g Hc is the gauge pressure at the centroid. Then you add it to the pressure at the free surface. So this is the total absolute pressure. Total absolute pressure multiplied by the surface area of this plate, which is A into B. This gives you the magnitude of the resultant hydrostatic force for a tilted. From this expression, you can directly obtain the expression for this vertically inclined case, because in this case theta is equals to 90 degrees, so sine theta is equals to 1. So this is the simplified expression for a vertical plate. Whereas for horizontal plate, you can directly write the expression. You know that the pressure here is uniform, so everywhere pressure is the free surface pressure plus rho g h into surface area. After obtaining the magnitude of the resultant force, next I will show you the point of application. We know that the expression which has been shown in the previous slide for the Yp is equals to Yc plus Ixx divided by Yc plus P naught divided by rho g sin theta into area. So Yp is equals to Yc. So this is, what is Yc? Y coordinate of the centroid, that is equal to s plus b by 2. So this is Yc plus Ixx c. So the moment of inertia of this plate about its centroid. It is, the plate length is A and perpendicular to this plane, width is, the length of this plate is B, perpendicular to this plane, the dimension is A. So for a plate of dimension A and B, the moment of inertia is given by A B cube by 12. So this is the moment of inertia in the numerator, and the denominator you have Yc, which is s plus b by 2 plus P naught divided by rho g sin theta, and then multiplied by area. So this is the expression for the center of pressure for a tilted plate. As discussed earlier, for vertical plate, sin theta is equals to 1, and then you can obtain the center of pressure for the vertical plate by substituting sin theta is equals to 1 in this expression. As I had mentioned earlier, the center of pressure for a horizontal plate is a midpoint, which is A by 2. Now let us take a special case where this vertical plate, the tip of the vertical plate is touching the free surface, or the height of the liquid is up till here only. Then in this case, so that is one simplification. Second thing what we are considering is the left hand side, you don't have this fluid. So let us suppose you have everywhere here atmospheric pressure. So as I discussed in the previous slide, so this is right now in this case on both the sides you have the same fluid. But let us take a simplified case where on the right side you have this fluid, On the left side, you have air where the pressure is atmospheric everywhere. So as I discussed in the previous case, that when we want to calculate the net hydrostatic force, where on one side you have a liquid and on the other side you have a air with everywhere where the pressure is atmospheric, then the atmosphere, due to the atmospheric pressure, there is a hydrostatic force which is acting on the left hand side. If you subtract that force from the right hand side, basically you have to consider the gauge pressure. So let us consider a case where we are talking about a vertical plate as a wall of a completely filled tank. This is the vertical wall of a tank where you have liquid on this side, you have air on this side, which is at atmospheric pressure, and this wall is completely filled till top. So we can subtract. So in this case, we can use the same expression which I have shown here, where we will not consider this P naught, and the resultant force in that case, and S equals to 0. So you get basically rho g a b square by 2, which is shown here, because S is 0 and P naught into AB cancels down, since on the other side you have air where, so the plate is exposed on one side at atmospheric pressure. So this cancels down because this resultant force is equals to force acting on the right hand side, which is as shown here. On the left hand side you have P naught into AB. So the net resultant force will be this force minus P naught into AB. So P naught into AB cancels down, S is equals to 0. So you get rho g a b square by 2 as shown here. Now the point of application also similarly, this S will be taken as 0, sine theta is equals to 1 since it's a vertical plate, and the P naught, this term is not considered due to the reason as I had mentioned earlier. So it becomes a b cube by 2, a b cube by 12 divided by S is 0, b by 2, this is not considered, b by 2 into a b. So it becomes a b square by 2 in the denominator as shown here. B by 2 plus a b cube by 12 divided by a b square by 2. So a b square cancels down from the numerator and denominator and you get b by 6. So it's b by 2 plus b by 6, which becomes 2b by 3 as shown here. So these are the magnitude of the hydrostatic force, and this is the point of application. If you have a tank which is filled till the top, so the tip is corresponding to the free surface, and on the other side you have atmospheric pressure on the other side of the wall of the tank. Note that these expressions which have been shown here will be used while solving the assignment and tutorial problems later. After discussing the hydrostatic force for the submerged plane surface, here the hydrostatic force on a curved surface is presented. Now the procedure which we use to calculate the hydrostatic force for the curved surface basically borrows the expressions which we had developed for the plane surface. So we reduce this problem of calculating the hydrostatic force on curved surface to a problem which involves the hydrostatic force on the plane surface. So using this overall strategy, the details are presented here. So in this topic, we will not do a separate derivations, but we will borrow what we have derived the expressions for the plane surfaces. So let us consider a tank which is made up of a vertical wall. This is the vertical wall, and horizontal wall. This is the horizontal wall, and the curved surface is as shown here. This is your curved surface. So we are not interested on what is the hydrostatic force on this vertical wall or horizontal wall. Our focus is on the force which acts on this curved surface. So what we do is that we consider only this curved surface, and as I mentioned, that we reduce the hydrostatic force acting on the curved surface to a problem involving plane surfaces. So what we do is that we take a vertical projected area. Vertical projection of this curve will be given by a vertical line here, and we take a horizontal projected area which will be given by a horizontal line as shown here. So note that our focus is only on the hydrostatic force acting on this curved surface, where AB is the horizontal projected area, BC is the vertical projected area. Now to calculate this, we'll do a derivation where we convert our calculation to calculating hydrostatic force on AB, which is like a hydrostatic force acting on a horizontal plate, and the hydrostatic force acting on BC, which is like a hydrostatic force acting on a vertical. How we do this? The details are presented here. We take this ABC. We take the fluid corresponding to this ABC as shown here, where AB is the horizontal projected area of the curve surface, BC is the vertical projected area. And this is, so we can take a liquid block corresponding to ABC, where AB is like a horizontal fluid surface, and in a horizontal surface we know the pressure distribution is uniform as shown here, and on a vertical surface the pressure distribution is linear as shown here. So this is the pressure distribution on this vertically projected area. So we are taking this fluid block, and I had shown you the pressure on the AB and BC. So we are drawing a free body diagram. Whenever we draw a free body diagram, on a static fluid, we are representing the various body and surface forces. So weight is a body force which depends on the volume of this fluid block. The pressure is a surface force. So I have shown you the pressure distribution on AB and BC. On this curved surface, actually the hydrostatic force that acts on the curved surface is the pressure on a surface acts inward. So the direction of hydrostatic force which acts on the curved surface is in this direction. But we are not considering, when we are drawing a free body diagram, we are not considering the force which is this hydrostatic force which acts on this curved surface. But when we are drawing this free body diagram, we take the force in opposite direction. So we take a reactive force which will be now we will show the pressure distribution in this direction. But actually, so basically you apply Newton's third law of motion. So you are considering on this surface the pressure is in this direction, on the curved surface the pressure is in opposite direction. The hydrostatic force on the curved surface acts in this direction. So these are the surface forces and body forces corresponding to this problem. And when we apply the force balance, we basically apply component by component. So let me first show you the net force on AB, BC and AC. So this is the net pressure force on BC, which is shown as Fx. The net pressure force on AB is shown as Fy, and the net pressure force on this curved surface is Fr. Now this Fr, when this is inclined, we consider its horizontal and vertical component. The horizontal component is denoted as Fh, vertical component is denoted as Fy, so Fv, and then when you do sigma Fx equals to 0, then we get this Fh is equals to Fx. So which indicates that the horizontal component of the hydrostatic force acting on the curved surface is equal to the hydrostatic force which acts on the vertical projection of the curved surface. Whereas when you consider sigma Fy is equals to 0, the weight will appear along with the Fv and Fy. So you get Fv is equals to Fy plus W. Finally, this expression leads to us to a statement that the hydrostatic force acting on the curved surface is equal to the hydrostatic force acting on the vertical projection. Note that this BC is a vertical projection of the curved surface, whereas the vertical component of the hydrostatic force acting on the curved surface is equal to the hydrostatic force acting on horizontal projection of the surface plus the weight. Note that here it is plus, but we can have situation where right now in this case the liquid is above this curved surface, but we can also have situation where liquid is below the curved surface. So let us say the liquid is in this below this surface here. Okay, so instead of liquid above, if I have liquid below, then in that case your horizontal projection will be here, and in that then the fluid column that you will consider, the fluid block will be the fluid region below this curved surface. Now on the horizontal projection, in that case the Fy, which is shown here as vertically downward, if the fluid is below the curved surface, it will be vertically upward. So in that case the weight and the Fy are acting in opposite direction. So in that case you will use Fv is equals to Fy minus W. So Fv, depending on the whether your fluid is above the curved surface or below the curved surface, you can have change in the sign of the weights. So with this, as I started the discussion saying that for curved surface we do not develop new expression. Basically we borrow the expressions which were derived for plane surfaces, because as you can see, we are to obtain the resultant hydrostatic force on a curved surface, we are calculating its horizontal and vertical component in terms of hydrostatic forces acting on the horizontal and vertical projections of the curved surfaces. With this, I come to the end of this lecture 10 on forces on submerged surface. These are some of the reference books corresponding to this lecture. Thank you for your attention.